This problem is on simple harmonic oscillations or simple harmonic motion. If you like, at this point you can pause the video and try to do the problem by yourself. I'm going to read the question now. A massless spring with spring constant K hangs from a ceiling as shown in figure A. So this is figure A. You can see the spring with spring constant K, and this is the same spring over there on the other side. When a mass M is attached to the free end of the spring, it attains equilibrium by stretching an E distance. So this E is what we call the extension. So mass M is attached to the free end of the spring and it stretches an E distance and becomes stable, or the system is in equilibrium. So then you can see this line, horizontal line, is what we call the equilibrium level. So at that level the spring and the mass are in equilibrium. The mass is experiencing gravitational force vertically downward, and that force is balanced by the spring force that is acting upward. Consider a situation where M executes vertical simple harmonic oscillations, or vertical SHM, with amplitude A. So amplitude is defined as the maximum displacement made by the object that is doing simple harmonic motions above the equilibrium level. So in this case, let's consider that the amplitude is less than the extension. So that's our assumption. So that means above the equilibrium level, if mass M is doing vertical simple harmonic motions, let's say that it's going downward. So it starts from the equilibrium level, goes downward and attains that maximum displacement, turns around, then goes through the equilibrium level, and then again it's going to attain maximum displacement on the other side and turns around and then crosses the equilibrium level again, and this motion is going to continue back up and down. So relative to the equilibrium level, in the upward direction, we can say that's the positive displacement. So I'll call that plus A. And below the equilibrium level, we can say that's the negative displacement. So that's minus A. And you can see the A value is below the extension. So our amplitude is always less than the extension of the spring after the mass M is attached. So there are four questions for this problem. The first one is asking, when M is moving through the equilibrium level, write down the total mechanical energy of the system. Now we need to identify what is the system for this problem. So the system for this problem includes two things, that is the spring with the spring constant K and the mass that is given by M. So spring plus mass is our system. So when the mass moves through the equilibrium level, so let me call that 1. So equilibrium level is denoted by 1. We want to find the mechanical energy of the system when it is at level 1. In second one, mechanical energy of the system when the mass is at the lowest level of vertical simple harmonic motion. You can see that's this level 2. So we need to find ME2 at level 2. And then part 3, when mass M is at the highest level of vertical simple harmonic motion. So that means this level 3, that's the highest level. So we want to find ME3, find the total mechanical energy of the system. Then the final part, show that this motion of the spring mass system obeys conservation of mechanical energy. So that means we need to show that mechanical energy at level 1 is equal to mechanical energy at level 2, and that's equal to mechanical energy at level 3. So if we can show that these are equal to one another, that means the mechanical energy remains the same. It does not change with time, it does not change with position. It's the same, meaning conservation of mechanical energy holds for this system. Now, when you write down expressions for total mechanical energy of the system, write down it in terms of the given the given constants here. So in terms of, so write down the expression in terms of spring constant K, mass M, extension E, amplitude A, and gravitational acceleration due to Earth, which we know as G. So write down those expressions in terms of these constants K, M, E, A, and G. So now let's try to do the first part of this problem. In the first part, it tells us to find the total mechanical energy of the system when the mass is moving through the equilibrium level. So initially you have the spring like this without any attachment to it, and then when you attach a mass M, the spring is gonna stretch an E amount from its natural length. So this change in length is E, and then it's in equilibrium. So this level is what we call the equilibrium level. The simple harmonic oscillations, the vertical simple harmonic oscillations, happens about this level. So that's our equilibrium level. So in the first case, in the first situation, they are asking what would be the speed of the mass when it moves through this level while executing simple harmonic motion. So that means you are going to displace it and then you are going to release it. As a result, it's going to move up and down. So something like this. So you will see motion like this. For example, starting from here, it's going to go down and then going to move upward, going through the equilibrium level, then turn around and then move down again, and then hit this maximum displacement, go through the equilibrium level again, hit the maximum displacement on the other side, and it's going to do this. So that's what we call this vertical simple harmonic motions. So this level is what we call the amplitude on the positive side, and this level is the amplitude on the negative side. When it reaches the amplitude, the maximum displacement level, you'll have the maximum acceleration. So this level, these two levels represent maximum acceleration and zero speed. I will call V as the speed. So zero speed is represented at these maximum displacement values. But at that level, you have the maximum acceleration. So again, over here, it's the same thing. Maximum acceleration happens at that level, and you have, at that moment, you have zero speed at that level. Then at the equilibrium level, then when the mass passes through the equilibrium level, you are going to see zero acceleration and maximum V or speed. So how do we find the maximum speed when the object is moving through its equilibrium level? So that's this speed. I'll call it Vmax. For this, we can use the equivalence of circular motion, uniform circular motion, and simple harmonic motion. So equivalence of UCM, uniform circular motion, and SHM. So what does that mean? So let's say that there's a particle that moves in a circular path like this, a circular path having a radius r. That's the radius and then this is the particle, and it's moving in this orientation. So that's the speed, and everywhere along this path the speed of the particle will be the same. So that's why we call it uniform circular motion. And if you look at the projection of this particle on a screen, let's say that you have a beam of light coming in this direction, so that's light. And then if you look at the projection of this particle, it's going to execute simple harmonic oscillations about this point, about this line. So it will start like this. It will reach the maximum displacement, which corresponds to the radius of the circular path, and it will reach the maximum displacement on this side, and then it will go through the equilibrium level. Again it will reach the maximum displacement on the other side. So it will go like that. So this simple harmonic motion is related to the circular motion that the particle is doing around this track. So for example, if we want to find the speed, maximum speed over here, say that this is the maximum speed, Vmax. So that's the Vmax, because over here V is 0 at these extreme points. You can recall we discussed this earlier, this is 0. Over here again at the extreme points V is 0, but V is a maximum when the object is passing through the equilibrium level. So this is equilibrium level. So what is the connection with Vmax and circular motion? So we can write for circular motion, if you recall, we can write this linear speed V is equal to the radius times omega, where omega is called the angular speed. It's called angular speed. So we can use that same relationship to obtain an expression for Vmax. So Vmax in SHM is Vmax equals, instead of R, you can see we can substitute the amplitude A for our SHM, simple harmonic motion. Amplitude A times omega. So Vmax over here corresponds to the speed of the mass, when it moves through the equilibrium level. Mass when it moves through the equilibrium level. Equilibrium level. So now we can use this information when we write the total mechanical energy of the mass as it passes through the equilibrium level. So this will help us to find the answer for part 1. So now we can write mechanical energy at level 1 for the entire system. As you know, it corresponds to kinetic energy at level 1 for the mass plus the potential energy due to gravity at level 1 for the system plus the potential energy elastic or spring for the entire system at level 1. Now the kinetic energy at level 1 is the kinetic energy of the mass, because that's the one that is moving. So 1/2 m Vmax squared. As I told you, the speed of the mass is a maximum when it passes through that level. So I put 1/2 m Vmax squared plus the gravitational potential energy of the system. Equilibrium level is considered as potential energy 0 level, potential energy due to gravity 0 level. So that means I can put a 0 over there. Then I have potential energy elastic or the potential energy of the spring, that is 1/2 k extension squared. So extension would be the change in position from the natural length of the spring. So that is going to be E. So I'm going to put E squared there, and then I'll make the substitution for Vmax. That would be 1/2 m A squared omega squared, because Vmax is A omega. So we square that term, and then we get 1/2 Ke squared. For a spring mass system, omega is called the angular frequency, and angular frequency is equal to the square root of the spring constant divided by the mass. So we can then substitute square root of k over m to omega. So this is something that comes from studying spring mass system. Angular frequency for a spring mass system. Sometimes this is called angular speed because, as I told you, it has this relationship with uniform circular motion. So sometimes it's called angular speed, but in this case I think it's appropriate to say angular frequency. So after substituting for omega, you are going to get 1/2 m A squared. So you can square this term omega squared, so that would be k over m plus 1/2 Ke squared. So then further simplification, you can simplify this further. M cancels out, and then you can factor out 1/2 k. When you factor out 1/2 k, you are going to end up with amplitude squared plus the extension squared. So this would be the simplified expression for the total mechanical energy when the mass passes through the equilibrium level, which I have denoted by 1. So that's how you do part 1 of this problem. In the second part, we need to find out the total mechanical energy of the system when the mass passes through the lowest point in simple harmonic oscillation. So if I draw the equilibrium level like this, then the second part of the question corresponds to when the mass is at the lowest point of simple harmonic oscillations. So that means this distance is going to be minus a. That's minus a, and this is the equilibrium level. So at this point, as I told you, there's no speed. The speed of the mass is equal to 0 because it's at this extreme point, the maximum displacement from the equilibrium level. So amplitude. So this is what we call the amplitude. So then again I can write, just like in part 1, mechanical energy, in this case it's level 2. So level 2, and if you recall, this is level 1. This again I can write kinetic energy at level 2 plus potential energy due to gravity at level 2 plus potential energy spring or elastic at level 2. The first term is 0 because there's no kinetic energy because the mass is at rest at that point, and potential energy due to gravity, if you recall, we measure potential energy due to gravity reference level as the equilibrium level. Okay, so then since level 2 is below the equilibrium level, I'm going to consider it as a negative potential energy. So that would be potential energy due to gravity is written as mg, separation of the vertical position. So m is the mass of the object, mg, instead of h I'm going to put a. Now remember, the negative sign is already there, so I don't need to put another negative sign here. So that's that negative potential energy. And then the spring potential energy of the system is due to the spring, so that means 1/2 k. Now the extension here, the extension is going to be from the natural length of the spring. So over here at this level 2, the extension is going to be E plus A. E plus A, because if you recall, the natural length of the spring was something like this. And this separation, we mentioned that this is E. So from that natural length for this level 2 position of the spring, the total change in the position is E plus A. This distance plus this distance, which is E plus A, and I have to square that term. So that's that expression. So I can write this as 1/2 k E plus A squared minus mga. So that's the second, that's the answer for the second part of this problem. Now, similar to the second part, I can write the total mechanical energy for the third part. Now, in this third one, we are looking at the topmost point. So this is the natural length of the spring without any attachment. And then you have this equilibrium position of the spring mass system when the mass is attached. So that's our equilibrium level. And also that corresponds to potential energy due to gravity equals 0 level. Now over here, as I told you, there's speed for this mass. Then it's going to reach the lowest point, and then it's going to move in the opposite direction. So this is this new position somewhere over there. So it's going to be below the below that natural position of the spring. And this separation is what we call, again, it's the amplitude. It corresponds to the amplitude of the simple harmonic oscillations. So however, since it's above the equilibrium level, I am going to consider it as a positive A. Below the equilibrium level, it's considered as negative A. So again, at this point, the speed is going to be 0 because it has reached the maximum displacement. So again, this is that amplitude. So looking at this, again, I can write the mechanical energy of the system at level 3. So now this is our level. So this is level 3, and if you recall, this is our level 1. That's again kinetic energy at level 3 plus potential energy due to gravity at level 3 plus potential energy due to spring at level 3. Just like in part 2, kinetic energy is 0 because it's at this extreme position, plus this one is going to be positive mgh. I'll simply write mga because our position or the new level is above the equilibrium level, where we considered the potential energy due to gravity 0. So mgA plus the spring potential energy of the system, which is due to the spring, the stretching or the compression of the spring. So that would be 1/2 K. Now here you can see this shows the natural length of the spring. So the new length, the new position is level 3. The separation between those two is going to be E minus A squared. So then we'll have finally 1/2 K E minus A squared plus mgA as the total mechanical energy of the system when the mass is at its highest point. So level 3 is for the highest point. So I'll write this over here: when the mass is at the highest point in its SHM. Over here in this part 2, when the mass is at its lowest point in its SHM. Okay, so that's important because you need to distinguish what are these two cases. One is for the highest point in SHM, and for the other one is the lowest point in SHM. The first one is when the mass passes through the equilibrium level, what would be the mechanical energy. So this is how you do part 1, part 2 and part 3 of this problem. Now let's do the final part of this problem, part number 4. Here we have to show that the mass that is executing vertical simple harmonic motion obeys conservation of mechanical energy. So that means mechanical energy at level 1 of the system should equal mechanical energy at level 2, and that should equal mechanical energy at level 3. So we need to show that this is the case in order for the system to obey conservation of mechanical energy. So from parts 1, 2 and 3 we obtain expressions for mechanical energy at level 1. For example, we got that as 1/2 K A squared plus E squared. And then for level 2 we got 1/2 K E plus A squared minus mgA, and mechanical energy for level 3 we got that as 1/2 K E minus A squared plus mgA. Now let me define this as equation number 1, expression number 1, expression number 2 and expression number 3. Now I'm going to show that 2 is equal to 1. So I'm going to start with mechanical energy at level 2 is equal to 1/2 K E plus A square of the entire thing minus mgA. Now let me expand the parentheses. I'm going to get 1/2 K. I'll have E squared plus 2 times EA plus A squared minus mgA, and this can be further simplified. 1/2 K, I'll have A squared plus E squared, and then I'll have this EA term, the second term in the parentheses. I can pull that out as KEA, because 1/2 and 2 cancels out, minus MGA. So we get to this point. Now keep in mind, when the mass is in the at the equilibrium level, so for vertical simple harmonic motion at level 1, when the system is in equilibrium, that is at a point like this, if you recall, that's the equilibrium level, and the natural length of the spring was such that it's like an E distance above this system when the mass is attached. So this was E, and we call this the equilibrium level. We should get from Newton's second law, net force on mass m should be 0, which means F net is equal to 0, and that implies KE minus mg is equal to 0. So KE is the force that is acting upward on the mass, that is due to Hooke's law. So this comes from Hooke's law. Because the spring force is magnitude wise, the spring force is equal to spring constant times the extension or the change from the natural length of the spring. So that's how we get KE, and that force according to this mass at the equilibrium level is acting in the upward direction, which balances out the weight of the object. So then we have this expression, KE is equal to mg, and I can call that number 4, my equation number 4. So you can see, coming back to this, I have 1/2 mechanical energy at 2, I have 1/2 k a squared plus e squared, and if I pull out this amplitude a because it's common, I have ke minus mg, and this is going to be 0 from equation number 4, because ke equals mg. So if you subtract mg out from ke, you are going to get 0, and then this is 1/2 k a squared plus e squared, which is nothing but equation number 1, or mechanical energy at level 1. So mechanical energy at level 2 is identical to mechanical energy at level 1. So that's shown. So this is something that we showed just now. Now we need to show that mechanical energy at level 3 is either equal to mechanical energy at level 1 or mechanical energy at level 2. So if we try to do that over here, mechanical energy at level 2, that is equal to 1/2 k e minus a square, the square of the complete thing, plus mga, and you can simplify that just like what I did earlier, and you'll see that 1/2 k, you're going to get a squared plus e squared, and then a minus ke a minus mg. It's a plus, actually it's a plus mGa. So just like the previous case, this is nothing but, if you factor out an a, you are going to get 1/2 k a squared plus e squared, and if you pull out this negative a, you are going to get ke minus mg, and that is again equal to 0 from equation 4, sorry. And this is again equal to mechanical energy at level 1 as a result. So you can see mechanical energy at level 1 is the same as mechanical energy at level 2, and that is the same as mechanical energy at level 3. So this should be mechanical energy at level 3, not level 2. So then this is satisfied. So that's how you show the final part of this problem, and this completes solving this problem.